And welcome to the lecture on Chapter 10. Here, we're going to talk about the interestingly titled Bizarre Stellar Graveyard. In other words, we're going to talk about what happens when stars die and what's left behind. Okay? All right. So, what is the Bizarre Stellar Graveyard? Okay? Well, there's a couple of states or types of stellar corpses that can exist. We've touched on these a little bit, so if they sound familiar, that's good. So basically, low mass stars like the sun, okay, so this is in the range of stars that are about a tenth the size or tenth the mass of our sun, up to stars that are about 3 times the mass of our sun. They're going to become white dwarfs after going through their final stages of becoming a giant, red giant, losing a bunch of mass on their upper surface, leaving a big nebula around them, which is called a planetary nebula, although it has nothing to do with planets. But eventually, they'll lose about 50% of their mass. There'll be no nuclear fusion left in their core. They'll have an inert core of oxygen and carbon, and that core will collapse into a white dwarf because gravity's going to push it in. Nothing's going to be able to, there's going to be no outward pressure, and what's going to be left behind is the white dwarf. But let's get to it, okay? What is the white dwarf, and what can happen to a white dwarf? Because it's interesting, they're not the end of the story when they're in a binary system. All right, so let's talk about this because it's definitely part of some of the key terms in this chapter. Okay, so here we're looking at a white dwarf. They emit a lot of rays in the X-ray spectrum. Okay, so they're not very hot. They're quite, they're not very luminous, I should say, especially not very luminous in the visible spectrum. They actually are fairly hot. They have a temperature which is going to be the same as like your big kind of ultraviolet main sequence, really bright stars. So, we're talking, surface temperatures on the order of 15,000 Kelvin. But not that luminous, okay? They're not emitting that much light because there's not much going on inside of them. There's, still some gradual gravitational collapse. There's still, basically they're cooling and they're just releasing energy through cooling. But they do emit quite a few X-rays, all right? So white dwarfs are the remaining cores of dead stars, as I said. Now, what holds them together? Is electron degeneracy, okay? And it's called electron degeneracy pressure, and it supports them against the crush of gravity. That's what keeps them from further collapsing and becoming a neutron star or becoming a black hole. They're protected from further collapse from the outward pressure of the fact that 2 electrons don't want to be in the same place at the same time. We actually discussed electron degeneracy when we talked about what brown dwarfs, basically failed stars, okay? Because in that case, fusion was never started because electron degeneracy pressure pushed back against gravity, and there wasn't enough gravity to overcome it, and the star stayed in a much cooler state without fusion. Okay, this is where the white dwarfs exist on the HR diagram, right? So we can see they have, basically it's actually this whole stretch here. And you can see their surface temperatures range between a little bit lower on the 8,000 Kelvin scale, well up into the 20,000 Kelvin scale. All right, they follow the planetary nebula phase, and they started with stars that were somewhere here on the main sequence. We've already discussed these stages of stellar geriatrics in terms of subgiants, red giants, and helium stars. Okay, so they're the eventual product of all these processes that take a couple billion years and leave us with a white dwarf, which again is just the leftover core from a mid-size or low mass star on the main sequence. The main sequence being a hydrogen-burning star. Okay? So white dwarfs, how small are they? Well, the core of the star that created them, a core of a star like our sun, was originally much more massive. But it did collapse during the cooling process that eventually creates the white dwarf, this process here, this part. And as it collapsed until electron degeneracy pressure eventually stopped it collapsing, that core became quite small. It became the size of the Earth. Okay? And interestingly, stars that have a mass about equal to our sun create a white dwarf that's about equal in radius to our Earth. Is it equal in mass to our Earth? Absolutely not. Absolutely not. It's actually equal in mass, the actual mass of the white dwarf. We could say mass white dwarf is equal to half the mass of the sun. Okay? So the idea there is because there was some mass lost in the process. So it was the star that created it had a mass of our sun. Now a white dwarf that is more massive is actually smaller because it's collapsed more. Electron degeneracy pressure is barely holding it together. It's reached the absolute limit. And 1.3 solar masses is the limit of the mass of a white dwarf. So this one actually has a mass of 1.3 M suns. Okay? And that's as massive as a white dwarf can be, because if it gets any more massive, then the electron degeneracy pressure can't prevent the collapse of gravity from causing a new physical process and a huge release of energy in that process. Okay? All right. And so interestingly, higher mass white dwarfs are smaller than lower mass white dwarfs. Okay. So quantum mechanics says that electrons must move faster as they are squeezed into a very small space. As a white dwarf's mass approaches its true upper limit of 1.4 solar masses, its electrons must move at nearly the speed of light. Okay? Once they start moving at nearly the speed of light, that's when that energy has to go somewhere. They start having more and more, because the electrons do have mass. As they move faster and faster, they have more and more what's called relativistic momentum, and that energy has to go somewhere, and eventually that energy is released. Okay? Because nothing can move faster than the speed of light, a white dwarf can never exceed that ultimate theoretical upper limit of 1.4 solar masses. The white dwarf limit, which is also called the Chandrasekhar limit, named after the astronomer Chandrasekhar, who was an astronomer in the earlier half of the 20th century, an Indian American, who came up with much of the ideas of both white dwarfs and neutron stars. Many of his theories, which have been very much matched the observations of the next 70 years. All right. Okay, so we got our upper limit of the white dwarfs. We got some rules about where they come from and their size, right? And they're these just really fairly hot, but not terribly luminous, but incredibly dense, strange corpses of stars. Okay. Now, what happens, however, when they're in a binary system? Because, for example, half of the 100 billion stars in our galaxy are binary systems. So that means that there are lots and lots of stars, including lots of very common, mid-size stars on the main sequence that become white dwarfs that are in binary systems. So it's very common for them to exist. And when they do, we can see something happens. There's a interaction between the mass of the other star in the binary system and the white dwarf. Okay? All right. So mass falling towards a white dwarf from its close binary companion, so it's not all white dwarfs, has to be one that's relatively close, has some angular momentum. That angular momentum means that that mass creates an accretion disk. So a disk forms around the white dwarf, or sort of adjacent to the white dwarf. It's called the accretion disk. And remember, accretion is just that term that means like gathering together. All right? So the friction between the orbiting rings of matter in that disk, that very high energy, high velocity, very energetic disk, transfers angular momentum outwards and causes the disk to heat up and glow. All right? And that disk heats up and glows and is very hot. And it definitely emits X-rays, which is part of that X-ray emission that we see, especially from white dwarfs and binary systems. So what would the gas in an accretion disk do if there was no friction? Well, it would just orbit indefinitely, okay? It would never lose any energy, and so it would just be a perfect sustained orbit. But since it does have friction, it is losing energy. It's losing that mechanical energy and thus slowing down, okay? So there's something called a nova. This is the first of our key terms here. Nova, supernova, and there's going to be two types of supernovas. So it's going to be a big focus. It's very much about kind of categorizing ideas in this chapter. So far we talked about one thing dead stars can become, white dwarfs, okay? Take note. Now we're talking about one process that dead stars can do, a nova, all right? So the temperature of the accreted matter eventually becomes hot enough for hydrogen fusion. The fusion begins suddenly and explosively, causing a nova. So essentially, here's that accretion disk, and that accretion disk is like a thin disk of matter, but it can get so hot that it reaches that limit of about 10 million Kelvin. Fusion starts, but there's nothing really to sustain the fusion. It's not like a thermostat inside of a working star, like when we talked about the thermostat of our sun, where gravity kind of pushes in and maintains the fusion rate. No, it's just totally unrestrained fusion. It's like a fusion bomb, okay? Because it's not just fission that makes nuclear bombs. There are also fusion bombs, hydrogen bombs they're called. Maybe you've heard of them. Well, fusion bombs, they're explosive. And that's what this is. It's essentially like a fusion bomb. It just blows up. And when it releases that explosion, that huge amount of energy, it emits a burst of light in different spectra. And astronomers have been seeing them for a long time, and they've named them novas. The historical name was because it was a bright flash. It didn't last that long. Astronomers noticed them periodically. They'd map them, discussed the wavelengths, and used prisms to split up the, we're talking 100, 200 years ago, split up the spectrum, analyze it, and at the time, astronomers mistakenly thought that that was the birth of a star. Because maybe it was a big flash. That was a star starting its life as a big hot burning ball of gas. Okay, right? Hence the word, because nova means new. Okay, and then there was the really big bright flashes, which got the name supernova. So again, 200 years ago, there was these two big bright flashes that astronomers weren't sure what they were. They were starting to understand at least what light was being produced, but they thought both of them had something to do with the birth of stars. They don't at all. Obviously, they have to do with dead stars, and specifically here, dead stars interacting with a neighboring star in a binary system. But regardless, that nova is a accretion disk, unsustainable hydrogen fusion flash. Right? That's what it really is. Right? They had no idea when they named it. Otherwise, they wouldn't have named it a nova, right? Okay. Another point is that novas can happen again and again, because they don't destroy the white dwarf. They don't destroy the companion star that's giving its matter over. They just kind of blow up the accretion disk. Well, over time, over maybe millions of years, that accretion disk can reform, and there can be another nova. All right. So the nova star system temporarily appears much brighter. The explosion drives accreted matter out into space. Okay, so it is a pretty large explosion. It definitely affects the whole interstellar medium, pushes some heavy elements and all these interesting processes, the intricate interactions between matter between stars. Okay, so what happens to a white dwarf when it accretes enough matter to reach its limit? Right, because we talked about it. That's absolutely the case. Something has to give when you reach the limit of 1.4, because then the electrons are forced to move at the speed of light, and they can't. Nothing that has matter, and electrons have matter, very little, but they do have matter. They cannot move at the speed of light. Only photons and other matterless particles, if they do exist, can move at the speed of light. Okay? Gravitational waves can move at the speed of light, but that's kind of the forefront of physics. We're not, but yes, So a few things can, definitely light. Well, what do you think? It explodes, right? Doesn't become a neutron star, doesn't collapse. That could be the case, but it turns out it's not. Okay? We'll talk about neutron stars and how they're formed. They're more massive than white dwarfs. But and maybe there are some conditions where white dwarfs can become neutron stars, but as far as astronomers know, what happens is that's not the case. Instead, they just blow up, okay? Because again, those electrons have so much energy that energy suddenly gets released and the star explodes. That creates a white dwarf supernova, okay? So there are two types of supernovas. So keep in track here. There's only one type of nova. A nova is a hydrogen fusion blast from the accretion disk of a white dwarf. Okay? A white dwarf supernova is a carbon fusion that suddenly begins in a white dwarf in a close binary system when it reaches its white dwarf mass limit, and it causes a total explosion. It's a one and done. Novas can happen again and again because accretion disk can reform, but the white dwarf supernova destroys the white dwarf. It is much brighter than a nova. Okay? There's a much bigger release of energy, spreads much more matter into space, spreads a bunch more heavy elements, causes fission of other elements, creating some of the missing ones in the periodic table, even causes energetically unfavorable fusion, creating other heavy elements. So it's a big deal. It's a huge event, a huge release of energy. A white dwarf supernova, and the supernova is gone, all right? Or the white dwarf is gone. Probably can significantly impact the binary star too, right? Not destroy it, but maybe rip off a huge amount of its outer layers of matter. Okay, but that is a totally different story from a massive star supernova, which we haven't talked about at all. And massive star supernovas have nothing to do with white dwarfs, nothing at all. This is a new topic. Okay, a massive star supernova is an iron core of a massive star that reaches the white dwarf limit and collapses into a neutron star. So it's a different process. And again, white dwarfs in binary systems don't collapse in neutron stars, but the mass that is inside of a big star, a much larger star on the periodic table, but on the HR diagram, it can actually become a neutron star. But it's a very different situation because that core in a massive star, it still has all the outer layers crushing down on it. And that's why it can become a neutron star rather than just blowing up. Okay? But we haven't really talked about neutron stars yet. We're just about to. But if we are talking about the two types of supernovas, and it makes sense, if we brought up one, we should bring up both. I agree with the book's approach here. There is one thing, is that astronomers can clearly tell the two types of supernovas apart because they have these distinct luminosity, versus time spectrums. So the way that they emit light over a period of a couple hundred days is you think, oh, they're kind of similar, but they are distinct. They're very characteristic. In particular, white dwarf supernovas always have this very defined peak and then a huge period of linearity. All right. Whereas massive star supernovas are much more complex. They kind of level off, and then they can become less luminous, and then they change again. And so, really, what astronomers look for primarily is that they look for this big period of real gradual decreasing in luminosity over time, and that tells them it's a white dwarf supernova. Okay. In fact, that's one of what's called the standard candles of measuring stellar distance, is the white dwarf supernova. Okay. And we'll talk about the mechanisms of measuring stellar distance very soon. We're getting there in terms of the chapters. So as the bullet point says, one way to tell supernova types apart is with a light curve showing how luminosity changes with time. Okay? And there's particular elements that are created that are distinct between the two events as well. All right, which you would find with the spectrum, the light spectrum, because remember every element has its own light spectrum fingerprint, the emission spectrum. Okay? So nova or supernova, let's compare, right? It's going to summarize the differences here. So supernova are much, much more luminous, about 100,000 times brighter than a nova. Novas are still bright, much brighter than just an average sun on the main sequence, right? But still nowhere near as luminous as a supernova, either type, okay? And we can see, right, both types of supernovas are nearly as bright, although the massive star supernova, it doesn't get quite as bright as the white dwarf supernova. Okay, the white dwarf supernova peaks out at a greater maximum luminosity, at 10 to the 10 solar units. That's crazy bright. Okay, so nova are hydrogen to helium fusion in a layer, right? So it's just like a layer of fusion in the accreted matter, right? And the white dwarf is left intact. Supernova is a complete explosion of the white dwarf with nothing left behind. Okay, all right. So supernova types, massive star, white dwarfs, they have different light curves and different spectra, as I said. Okay, so in summary, a white dwarf is the inert core of a dead star. Okay, what type of star? A low mass or mid-mass star. Electron degeneracy pressure balances the inward pull of gravity. That's how the white dwarf can be sustained. All right. What can happen to a white dwarf in a close binary system? Matter from its close binary companion can fall into the white dwarf through the accretion disk. The accretion matter can lead to a nova and a white dwarf supernova. Because in both cases, I want to make that clear. I don't think I did as well, but I want you here, is that the accretion disk, okay, that causes the nova, fusion in the accretion disk, but also some of that matter falls into the surface of the white dwarf. That's how the white dwarf actually can get more massive, and how it can get up to that point where it leads up to that point of having a mass of 1.5, solar masses, right, and then eventually is forced to explode. So that's the idea, is that the accretion disk and some of that matter that doesn't stay in the disk but actually settles onto the surface of the white dwarf. That's what can, not always, can lead to the white dwarf supernova. In a sense, it's almost like if a white dwarf in a binary system can have a nova, that's a way of sort of like keeping itself alive, because then that matter blows away and then it's not in danger of becoming so massive that the whole thing blows up. So, you can almost, and I'm sure there are cases where a white dwarf can avoid ever having a white dwarf supernova by continuing to have novas and the accretion disk blowing up. And that's all due to some, intricate balance of how far the binary star is away, how much matter it's shedding, and all these factors that would lead to these, various processes. Okay, so we'll talk about neutron stars, but real fast. If you're wondering, what about white dwarfs that aren't in binary systems? There's plenty, right? Or what about white dwarfs that are, they're in a binary system where the other star is so far away that it's not really, giving any matter to its accretion disk? Well, in that case, the white dwarf just continues to shine, kind of fairly low luminosity, quite hot, very massive, and it will continue to do so for billions of years. Now, the theory and the models suggest that after about 100 billion years, so maybe 10 times longer than the current age of the universe, so kind of unfathomably long time, the white dwarf will eventually cool and it will become what's called a black dwarf, which is really can be think of as a giant, very dense crystal. And it'll just become totally cool, but incredibly gravitationally intense. So you couldn't like land on it because you'd be crushed by the gravity. But it'll just be this huge, cool, gravitational source. Not like a black hole in terms of like nothing can escape. You could escape. You just have to be very sturdy in order to withstand the incredibly strong gravity. And by incredibly strong gravity, I mean like 1,000,000 times greater than the gravity on Earth. 1,000,000 times greater. All right, that is crushing gravity. All right, but that's the theorized eventual end state of a white dwarf that isn't in a binary system. Okay. All right. So now on to neutron stars. We've mentioned them a little bit in the massive star supernova, but now we're going to get into them in more detail. What is a neutron star? How were neutron stars discovered? And what could happen to a neutron star in a close binary system? Kind of similar question to the white dwarf question. Okay. All right. So here we're looking at a neutron star. So a neutron star is the ball of neutrons left behind by a massive star supernova. Okay. Massive star supernova. Okay. Star collapses. There's basically, and we talked about that end state of massive stars, they get that inert iron core. The iron cannot undergo fusion and create energy. In fact, if it gets hot enough for fusion to occur in the iron core, that's called the iron catastrophe, because when it starts to fuse, it actually eats up more energy than it produces, just speeding up the gravitational collapse. And that's when the supernova happens, the massive star supernova. But what's left behind, there is still all that matter. Nothing can really push that incredibly dense matter that's left behind away, and so it just continues to collapse. It collapses right past the electron degeneracy pressure limit because there's enough outer layers to force it to do so, and it reaches a new degeneracy pressure limit, that of neutrons themselves. All right? And that supports the neutron star against gravity. And a neutron star, compared to a white dwarf, is much, much smaller. It's about 10 kilometers across. That's the diameter of a neutron star. And that's compared to the diameter of a white dwarf, which is about 12,000 kilometers. All right? For white dwarf, WD. Okay? So much, much smaller. Very, very different physics holding a neutron star together. Because what's happened is when the electron degeneracy pressure is overcome, again, electrons can't travel greater than the speed of light, but something else can happen other than them just blowing up. The electrons can actually fuse with protons and become neutrons. So the plasma, because the plasma that was there was a plasma of just pure protons and electrons, because any molecules would have been dissociated. And in fact, yes, there are some heavier elements, but it's just pure, kind of groups of protons, many of them just single protons, because that would be the nucleus of hydrogen. Some of them, larger groups of protons, which would represent the nucleus of heavier elements like, helium and carbon and so on. But just groups of protons packed together and a bunch of free electrons all packed together in this highly dense plasma. Plasma is an ionized gas, okay? But when it's pressed together even more, and electrons can't go anywhere and can't travel faster than the speed of light, their wave matter state actually becomes one with those balls of protons, and they all become neutrons. All right, leaving no electrons or protons behind, because that's possible. Neutrons can decay into protons and electrons. That's called beta decay. It's a known process, and it's theorized that we can't exactly observe it, right? Directly observe it, but it's theorized, and it matches the models that's what happens in these leftover cores of massive stars, and that's what a neutron star is. It is pure neutron matter. Okay, so here's the idea. Electron degeneracy pressure goes away because the electrons combine with protons, making neutrons and neutrinos. Okay, neutrinos are a release of some of the angular momentum in the form of a particle. Okay, a very, very low mass particle. Actually, its mass is unknown, although we do know it must have mass due to some properties that it shows in its behavior. So the neutrons collapse to the center, forming a neutron star, just a dense core left over. Okay, all right. So how were neutron stars discovered? Before I go there, I do want to say one thing, because people always ask this: where do neutrons show up on the HR diagram? Well, they don't. Okay, they're basically off the HR diagram. They have a very high surface temperature. They're very, very dense, and they're not very luminous in the visual spectrum. And one reason for that is because they actually don't release much light, because their mass is so great that the escape velocity almost matches the speed of light. And so light is restricted along very, very particular pathways, also due to their incredibly strong magnetic field. And at least, the charged particles that emit light, that the acceleration of the charged particles that further emit light. Because, of course, the light itself is not affected by the magnetic fields, by the way. Light is never turned by a magnetic field, nor electric field for that matter. But they just don't fit on the HR diagram. Okay, so you're never going to see a neutron star on the HR diagram just because of the exotic way that they emit light. Okay, all right, but let's use that as a segue, because how do they emit light? They emit light in pulses as we observe it. Okay, now it turns out they're not actually pulsing, but they appear to be pulsing. All right, so pulsars were discovered a while ago, and astronomers didn't realize at first that pulsars and neutron stars were the same thing. A pulsar is a star that flickers. Okay, not because of our atmosphere or anything. We can observe it in a space-based telescope, and we can actually see it. Its intensity, its luminosity going up and down a few times per second. Sometimes it can have a period of pulsing of one time per second, like pulse, 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 pulse. What could cause that? What could cause a star to pulse so frequently and with a pretty significant change in intensity? Well, using radio telescopes in 1967, Jocelyn Bell noticed very regular pulses of radio emission coming from a single part of the sky. The pulses were coming from a spinning neutron star, a pulsar. All right? So here's a time-lapse image of the pulsar in the heart of the Crab Nebula, the remnants of a massive star supernova. Okay, so that led some credence to maybe the pulsar has something to do with the supernova. Maybe there's something that's left over from the supernova. But why would a leftover neutron core of a star be pulsing? Well, it's because it's spinning and because the light, the beamed radiation, is restricted along basically one path. This is like there's no light that is emitting off to the sides. The light is absolutely restricted to the single axis. All right. So a pulsar is a neutron star that beams radiation along a magnetic axis that is not aligned with the rotation axis. So you can kind of think, because a lot of times you think of Earth, and its magnetic axis has to be aligned along its rotation axis because it's like a dynamo. It's creating its magnetic field through its rotation. All right. But a neutron star is so dense and there's so much matter and so much energy packed in it that it's more like a permanent magnet. And so it's like a permanent magnet that's spinning, and you can spin a permanent magnet. Like imagine like a fridge magnet or one of those magnets you'd seen at a school laboratory. You could spin that thing so it's spinning not along the axis of its magnetic field, the north-south pole, and that's it, right? There is a north-south pole, so north-south, but that's not. Those poles are not aligned with the rotation axis, and so what happens then, since the light is restricted because of the way the light is emitted from very fast accelerating charged particles, it is restricted along that magnetic field line, and thus we see it passing over us. It's like a lighthouse, right? So here's a lighthouse, right? You'd see the beam of the lighthouse. So if you're looking dead on at the lighthouse, you'd see flash, 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 which with each half turn of the lighthouse. Likewise, here's an artist's rendition of a neutron star. You see that beam of high energy light coming from the neutron star, pulse, 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 when you look head on at it. Okay? So the radiation beam sweeps through space like a lighthouse beam as the neutron star rotates. Pretty amazing. Okay? All right? So why do pulsars must be neutron stars? How can we confirm that these two things are the same? Right? Well, the circumference of a neutron star is 2 pi radians, about 60 kilometers. Okay? Right? On the large side, they can be as small as 10. The spin rate of fast pulsars is about 1,000 cycles per second. Well, the surface rotation velocity then would be 60,000 kilometers per second, using some basic physics to relate those quantities, which is about 20% of the speed of light. All right? So that would be escape velocity from a neutron star. All right? Well, here's the thing. That's so fast that it can't be any other form of star. If it was a normal main sequence star, or let alone like a red giant or any other star we know of, or even a white dwarf for that matter, it would be torn apart. Even a white dwarf, if it was spinning that fast, it couldn't hold together. The gravitational force would not be great enough. We talk about gravitational force crushing, right? But neutron stars spin so fast due to the fact that they're so small and they have so much leftover angular momentum that if they were made of anything else other than pure neutrons, they would tear themselves apart. So they must be a neutron star. The physics says, is unequivocal on that. Okay? So pulsars must be neutron stars. Right? So they spin fast because a stellar's core speeds up as it collapses. That's conservation of angular momentum. It's like the ice skater pulling their arms. But in this case, it's like the ice skater pulling their arms and then collapsing down to a point smaller than a pinpoint. Right? If we were to kind of make an analogy, right? All that matter collapsing at one point. Imagine how fast it would be spinning. All right? So that's conservation of angular momentum, but on an incredible scale. All right? So could there be a neutron star that appears as pulsars to other civilizations but not to us? Think about a lighthouse. Could you imagine a lighthouse that someone could see as a pulsing lighthouse, but someone else wouldn't see as a pulsing lighthouse? Well, yeah, right? Because, what if you were like in a hot air balloon directly above the lighthouse? It wouldn't appear to be pulsing at all, would it? In fact, if the thing about the lighthouse, you can kind of see the light because you can see it like reflecting off of like maybe like fog in the air, right? So you actually kind of like see the beam. Well, that's not the case with the neutron star, right? It can be, I guess, if it interacts with like nearby nebula or something. But for the most part, you either see that light hitting you or you don't. So if you're directly above a neutron star and it's spinning in a plane that is perpendicular to your line of sight, then the neutron star would be invisible to us because you wouldn't see the pulses. The pulses would be off to the sides, and none of the pulses would face us as an Earth-based observer or a other civilization-based observer, the aliens, right? And so that means that we don't see all pulsars, and pulsars that we see, other planets and other solar systems might not necessarily see. Okay? So, now, back to the binary system, right? Got a similar question that we asked with the white dwarf. But what happens to a neutron star in a close binary system? Well, it's incredibly dense, so you better bet it's going to pull matter off of any nearby star, just like the white dwarf did, and even more so, right? Because it's even denser, right? So what does it do? It creates an accretion disk. Really, same idea, right? It creates an accretion disk, just a more dramatic one than a white dwarf. All right? All right? So the accretion matter adds angular momentum to a neutron star, increasing its spin. All right? And according to the conservation of angular momentum, what would happen if a star orbiting in a direction opposite the neutron star rotation fell onto a neutron star? Would it speed up, slow down? It would have to slow down because it would lose a little bit of its angular momentum. There would actually be a torque exerted in the opposite direction on it. All right? So the matter accreted onto a neutron star can eventually become hot enough for helium fusion. All right? Now that's a different type of fusion. When we talked about the nova that was caused by the accretion disk of a white dwarf was basically a unsustained hydrogen fusion event of that entire accretion disk. But the accretion disk of a neutron star is different, it's denser, and instead hotter, thus helium fusion can occur. And it turns out that the sudden onset of helium fusion produces, instead of a burst of light like a nova, it creates a burst of, at least visible light, it creates a burst of X-rays. So when we talk about X-ray bursts, we're talking about sort of like neutron star novas, but they're not called neutron star novas, they're called X-ray bursts. But just like novas, X-ray bursts come from accretion disks, but unlike novas, they come from the accretion disks of neutron stars. Okay? So again, things to keep track of. X-ray bursts are caused by the accretion disks of neutron stars. All right? So, what have we learned? A neutron star is a ball of neutrons left over from a massive star supernova. It's a leftover core. Okay? It's supported by neutron degeneracy, not electron degeneracy. Okay? It's a pressure that pushes back against gravity. All right? The beams of radiation from a rotating neutron star sweep through space like a lighthouse, making them appear to pulse. Okay? And again, we didn't really talk exactly about, why neutron stars have beams like that, why they have such a strong magnetic field. But again, just kind of like think that they're so dense, that the matter is so exotic that it's able to do things that normal matter couldn't. Okay? And observation of these pulsars were the first evidence for neutron stars. That's how we kind of first, wonder what they were, and then eventually associated them with supernovas and the leftover cores of dead massive stars. Interestingly, neutron star, the matter that makes them up, is so dense. It is so unlike ordinary matter. Even dense things like lead or uranium, right? These dense elements that exist, right? That if you were to get a sample of pure neutron matter, the stuff that these neutron stars are made out of, that are a few kilometers across, if you were to get a small sample of that matter, like a spoonful of it, and somehow either produce it on Earth or bring it back to Earth, there'd be no way to restrain it. It'd be so heavy that it would pass through any ordinary matter, no matter what. You could put it in a bowl made out of like pure uranium, or pure titanium, the densest, strongest bowl you could imagine, and it would just tear through it, and it would accelerate, tearing through, causing a huge release of thermal energy, ripping a hole through the entire Earth, then slowing down due to once it passed through the core of Earth, it would start experiencing acceleration the opposite way, so it would gradually slow down, again, just like melting everything in its path. And then, kind of then reach the other side of Earth, having ripped through the center of Earth, and then slow down to arrest, and then turn back around and go the other way, ripping back through the center of Earth, and just oscillate back and forth, tearing a constant hole back and forth through the center of Earth, creating tiny black holes in the process. All right? So, could potentially, a spoonful of a neutron star could eventually lead to the destruction of Earth. That little. Okay? Or at least a huge region of Earth that would be unusable on either sides of the core, either sides of the core. So you can imagine like a forbidden zone on one side of the planet and another forbidden zone on the other side of the planet that no one could ever do anything with because there'd be huge releases of radiation and uncontrolled thermal energy being released and like fires and all these things as this matter just oscillated back and forth. Okay, so yeah, pure neutron star matter is no joke. All right. So, and then as far as the binary system, the accretion disk around a neutron star can become hot enough to produce X-rays, making the system an X-ray binary. That's a term in astronomy. Sudden fusion events periodically occur on the surface of the accretion disk, producing X-ray bursts. And they occur much more frequently than novas, by the way. All right? All right. So then on to black holes, right? The elephant in the room. We've talked about two things that dead stars can become: white dwarfs, neutron stars. But it turns out that there's another thing that can happen. If the star is big enough and neutron degeneracy can't fight against gravity, then gravity wins and a black hole is created. Okay? And black holes are very different. Neutron stars, they're exotic. Yes, right? Hard to understand sometimes, they're so exotic. But black holes are a whole nother level of mystery. All right? What is a black hole? What would it be like to visit a black hole? And do black holes really exist? Okay? So, what is a black hole? Well, a black hole is an object whose gravity is so powerful that not even light can escape it. So a black hole has something called the event horizon. The event horizon is the point where the gravity of that collapsed core from a star is so great that the escape velocity is greater than the speed of light. Thus, nothing can escape because nothing is faster than the speed of light. All right? So what happens to the escape velocity for an object if you shrink it? Right? Well, it increases. And if you continue to shrink it, eventually that escape velocity becomes so great that it becomes the speed of light. All right? So light would not be able to escape Earth's surface if you shrunk Earth down to the size of less than 1 centimeter. So in other words, if you could somehow turn Earth into a black hole, it would become a 1 centimeter black hole. Right? If you took all the matter of Earth, all the mass that makes up Earth, and collapsed it down to 1 centimeter, it would then become a black hole. And two things then would happen. It would then have that event horizon, a radius of 1 centimeter, of which nothing could escape, no information, no light, because information itself is light. Think radio waves, think microwaves, right? Every type of beamed information uses light, all right? Furthermore, the mass itself would just continue to collapse. So somewhere within that 1 centimeter would be a point that would be infinitely small called the singularity, because nothing could stop that collapse of matter. And so there's two things about the black hole. There's the point of no return, the event horizon, with escape velocity greater than the speed of light. But then somewhere within is this, maybe even stranger than the point of no return, is a point of absolute density that is infinitely small. Okay? So the surface of a black hole is the radius at which the escape velocity equals the speed of light. Okay? And again, surface is in quotes because it's not like a solid surface. It's just the point of no return. This spherical surface is known as the event horizon. All right? The radius of the event horizon is known as the Schwarzschild radius, because Schwarzschild was the physicist that first quantified the event horizon. Interestingly, it was the first time that Einstein's general theory of relativity had been used to get a numerical result. Einstein himself didn't use his own theory to get a numerical result until after Schwarzschild again. Also, Schwarzschild did it while dying. Due to sicknesses that he picked up in I think World War I, but he did this first calculation using this new theory. This was in the 1920s, and the theory was published in 1919. And so here we had this idea, the Schwarzschild radius, and so that's why we call it the Schwarzschild radius. But it's just the radius of the event horizon, okay, which is a sphere of no return. Okay, so a black hole's mass strongly warps space and time in the vicinity of the event horizon. Okay? That means that if light passes even near a black hole, it will be significantly affected. It will experience what's called a gravitational redshift because it will actually slow down relative to other observers. So in other words, time passes more slowly for everything that's close to the black hole. And one effect of time passing more slowly is the natural oscillation of light being a wave, causes the frequency to increase, or the frequency to decrease, thus increasing the wavelength. And an increased wavelength is a redshift. Now we've talked about redshifts. If something moves away from you, it has a redshift. If something moves towards you, it has a blue shift. That's the Doppler effect. Well, this is a redshift that has nothing to do with relative motion, so no Doppler effect. This is a redshift that's due to the warping of space-time itself. So we call it a gravitational redshift. All right? So nothing can escape from within the event horizon because nothing can go faster than light. All right? That's why it's the point of no return. No escape means there's no more contact with something that falls in. It increases the hole's mass, so it actually will change the radius. So if you have a black hole that is, say created from Earth, right? Couldn't really create a black hole from Earth because there's not enough matter to collapse it into a black hole, but if somehow you could, you'd have that 1 centimeter black hole. Well, if you throw another Earth's mass, mass of Earth into that 1 centimeter black hole, it would increase in size. It would be its radius wouldn't be double, but it would be proportionally larger. All right, okay. So quantum mechanics says that the neutrons in the same place cannot be in the same state. This is the neutron star limit. That was that neutron degeneracy. So the neutron degeneracy pressure can no longer support a neutron star against gravity if its mass reaches 3 solar masses. So think of this as the equivalent of the electron degeneracy limit, which is 1.5 solar masses. That's when white dwarfs went white dwarf supernova. Okay. Now we have another similar limit, which is the limit of neutron stars. So if neutron stars exceed that limit, then they fail to become neutron stars, and instead they become black holes. So some massive star supernovas can make a black hole if enough mass falls into the core. All right, so that's the idea, is that when you have a massive star supernova, there's going to be one of two things left behind: either a neutron star, which we discussed before, or a black hole, which we're currently discussing. Okay, now that's so in a very so like the origins are kind of like they're not so bizarre, right? Like, okay, you either create a neutron star or you create a black hole. But the black hole is so much stranger than the neutron star, right? Because it truly just breaks physics. It is so hard to understand what it really represents. Okay? So beyond the neutron star limit, no known force can resist the crush of gravity. According to the general theory of relativity, that's Einstein's theory published in 1919, gravity crushes all the matter into a single point known as a singularity. So that would be a single point within the event horizon. And its diameter would be infinitely small, as I said before. The quantum physics predicts a different scenario near the center of the black hole, and we're not sure which it is. We're not sure what the singularity truly is, because there is no agreed upon theory. There's no unified theory in physics that tells us what that singularity truly is. Okay? All right. So how does the radius of event horizon change when you add mass to a black hole? Okay, we mentioned this before. It increases. Okay? So what would it be like to visit a black hole? Well, they don't suck you in, okay? So you can orbit a black hole just like orbiting a star. So if the sun became a black hole, its gravity would be different only near the event horizon, right? So you have to be very, very close to experience essentially like tidal forces, kind of like we have tidal forces between us and the moon. And if you're further away from the black hole, you can just orbit it normally. So you can definitely have planets around a black hole. Those planets probably wouldn't be great for life because the black hole emits a huge amount of X-rays, although the X-rays are beamed off, kind of like they're beamed off from a neutron star. So as long as you're not in the path of the beam, you may be okay. All right. Near the black hole, space-time is significantly warped. Straight lines are not straight. All right. So light waves take extra time to climb out of the deep hole in space-time, leading to that gravitational redshift I mentioned. So that's also true if you are really close to a black hole, time would move much more slowly for you. The movie Interstellar did this very well if you saw it. If you were on a planet that was near a black hole, 1 hour for you could be 1 year for someone back on Earth. Okay, that is the warping of space-time. Okay, time does not pass the same in every reference frame. Okay, that's both true if you move very quickly, or in this case, if you're near a large gravitational source. It even applies to not large gravitational sources. There is a very small but important difference in the passage of time on the surface of Earth and in orbit 300 kilometers above the surface of Earth. And that actually has to be accounted for the accuracy of GPS satellites. Okay? General relativity is used for the accuracy of GPS satellites because time for them runs slightly faster than it does for people on the surface. Okay? All right? So time passes more slowly near the event horizon. All right, and is it easy or hard to fall into a black hole? Quite hard, right? You have to kind of head straight for it, and even then, you're probably just going to take an elliptical orbit around it. All right, so it doesn't suck you in. Okay, so what if you actually were to approach the event horizon? Well, the tidal forces near the event horizon of a 3 solar mass black hole would be lethal to humans. All right, because it's a black hole, the event horizon, the actual calculated Schwarzschild radius of this very, very smallest possible size of a black hole, is about 1 kilometer. So it's incredibly small. And so that means that there's a huge amount of actual variation in the forces, which it would cause you to be stretched. And so it would tear apart your molecules, okay? It would tear apart anything, even like, if you put a metal rod and you push it towards one of these, these 1 kilometer radius, smallest possible black holes, which do exist, that very metal would get stretched. So the tidal forces would be gentler near a supermassive black hole because its radius is much bigger. We'll talk about supermassive black holes. There are supermassive black holes that are 100 times bigger than the radius of our own solar system. So they're a very, very different kind of black hole. Essentially, they're a black hole that exists on a galactic level. There's only one such supermassive black hole per galaxy as far as we can understand, okay? So do black holes really exist? Yes, they do, okay? So we need to measure mass by, here's the verification. We need to measure mass by using orbital properties of companion stars, measure the velocity and distance of orbiting gas. It's a black hole if it's not a star and its mass exceeds the neutron star limit, okay? There's nothing else it could be. All right, so some X-ray binaries contain compact objects with mass greater than 3 solar masses, so they can't be neutron stars. They have to be black holes. They have an accretion disk, like a neutron star or a white dwarf for that matter. They have X-ray bursts, but their mass is too great. They have to be a black hole. All right, and we don't see light coming from them. And you might be like, oh, maybe they're just a pulsar, but the pulse is facing away from us. Nope, can't be the case because that mass. Okay, all right. So one famous X-ray binary with a likely black hole is constellation Cygnus. Okay, right here, there's the black hole, Cygnus X1. So in summary, a black hole is a massive object whose radius is so small that escape velocity exceeds the speed of light. Okay, that's the event horizon, the point of no escape. Okay, the point of no return. You can orbit a black hole like any other object of the same mass. Okay, black holes don't suck. Near the event horizon, time slows down and tidal forces are very strong. Okay, and yes, they exist. We can see their confirmation of their existence in X-ray binaries. All right, well, that's it for our 3 types of dead stars: white dwarfs, neutron stars, and black holes. All right, so I hope all these facts were interesting and informative. Thank you for watching.